Yeah, but test 3 was weird. There wasn't a lot to do, so if you made a minor mistake, relatively, you got a lot of points taken off, just because there were only like 3 problems or something. So every mistake is a bigger mistake, but anyway. So what we're going to talk about today is power series, but could you tell me, for example, tell me about the convergence of that guy. Yeah?
Can you say that it's always less than or equal to 2 over n squared plus 1?
Okay. And how would you say that?
And then see if that converges. Which it does because it's a p-series.
Okay. So you'll say that cosine squared n plus 1 over n squared plus 1 is less than or equal to 2 over n squared plus 1. So we know that the series of this must be less than the series of that. And what can we say about this guy?
That it's less than the series of 2 over n squared.
This is again less than 2 over n squared. And this guy,
Is it convergent?
Convergent p-series.
convergent p-series, which means alright, so like if I call this S converges. Yeah, but specifically how? If you had to, what kind of convergence? Give me a full.
Absolutely.
You would say it converges absolutely, because if you put absolute values around this, it would literally make no difference to anything, right? Right, cosine squared plus 1 is positive, and it's true to say this. Technically, you should know that if you have sum like this, it's less than or equal to, you'd have to split up the sums individually. That's something called like the triangle inequality. But it still applies here. The biggest this could be is 1, so the largest the top can be is 2. And everyone's squared, everyone's already positive, so literally taking an absolute value is making no difference whatsoever. So you would say this converges absolutely. Right? And that would be the first thing you always check. So you always want to check if something is convergent absolutely or not. Okay. I just wanted to see if you guys are looking at it the right way. There was something on the test, I think. It's -1 to the n. N factorial over n to the n. Something like that?
Yeah.
What did you conclude from that?
Divergence.
It diverges. How did you know?
Oh, because cosine is always me.
Huh?
Cosine.
the limit of that guy is 0, because we know factorials are equals n to the n. Factorials grow a lot slower than this guy, so that goes to cosine of 0, which is 1, which is not 0, so you just use the test for divergence. Yeah, so that was very similar to the one on the review. Okay. Was there anyone that you guys were confused about? We can do that quickly.
All of them?
All of them? All of them? Can't do all of them. None stuck out, they were all equally, they were all like, oh my god. Okay. We're going to move on to, I forgot what section, it's 11.5, I think, power series. definition, a power series is a series of the form an x minus x naught to the n. Okay. Now basically if you write that out, what you'd kind of see that looks like is a0 plus a1 times x minus x naught a1 plus a2 times x minus x naught squared plus a3 times x minus x naught cubed plus da da da. In fact, the idea is it's an infinite polynomial. And polynomials are nice. They're very nice to do calculus with. We can integrate them easily. We can differentiate them easily. They're continuous everywhere, all that nice stuff. So we're now going to use an abstraction of a polynomial to start making series more useful to us. And the power series is going to be the first stop. This is called the power series. And it's centered at what we call x naught. You could also do a power series centered at 0, and that would look more like the typical generic form of a polynomial. So your power series would look like a n x to the n, and goes from 0 to infinity, which is your a0, a1x plus a2x squared plus a3x cubed plus da da da. So that would look more like your generic polynomial, but it goes on forever. It's an infinite degree polynomial. Yeah?
Why do you have to write x minus x naught?
Because sometimes we want it to be able to center it at some point. So it's sort of like when you write down the equation of a circle, how that subtraction from the x-coordinate tells you, oh, the center is moved this way. Sometimes we want to consider a polynomial, but we don't necessarily want to consider it in terms of x, but rather some shifted polynomial. So we want the freedom to be able to shift our polynomial to be centered at some value.
And x is not.
And x is just like x, like the generic x value on the x-axis. Yeah. So x is actually a variable here, right? In the sense of you can think of it as the input variable for some function, but I can write down an infinite polynomial in this way, right? So as far as the series is concerned, the x is not a variable, the n is the variable, but in the broader context in which you're going to be considering this, the x is the input variable for you. You're just using a series to be able to write down this kind of expression for shorthand, as well as it will help us talk about a lot of nice things based on what we know about series. So that's called a power series. I didn't jump into examples right away, but let me just mention. We also like to know where such series converge. We typically do this. So when it comes to a power series, I can ask you where something converges. By the way, it's emphasis on where as opposed to if. And I'm gonna show you how we actually deal with that. We typically use the ratio test to talk about this. Now, you can use other tests in general, but the ratio test is nice because it also tells us about absolute convergence at the same time, and it gives us a nice little inequality that we can play around with and sort of talk about the range of the x values. So let's do some examples. Maybe another definition here. The interval on which these series converge IOC. If the IOC is of finite length, then half the length is called the radius of convergence. And I'll give you a different characterization of this idea as well. But sort of like if you measure from the center, which is at x0, and you can measure to one end of the interval of convergence, that's called the radius of convergence. So your x0 is here, where the series is centered. And let's say the series converges on some interval that goes from here to here. So if the series converges on that, then this distance here is called the radius of convergence, the ROC. And this entire interval I above is the IOC. So now let's look at some examples, because that might be too theoretical. Determine the interval of convergence of the following. So I'm going to give you some power series, and you're going to tell me on what interval they work. We're just going to look at 3 for now. The series from n equals 0 to infinity of x to the n. The series from 1 to infinity of x minus 4 to the n over 2n. That's B. C. The series of x to the n over n factorial from 1 to 0 to infinity. So say you're given a power series, and I can ask you, what is the interval of convergence of this power series? I can also talk about the radius of convergence, but I want to say something more about that. Meaning, if this series converges, where will it converge? And by the way, it turns out a power series will always converge, and I'll give you a theorem that tells you exactly the conditions for that. Notice that if I plug in x equals 0, that converges, right? And x is a variable that I can manipulate. Plug in x equals 0 here, that will converge. If I plug in x equals 4 here, that will converge, right? There's always going to be some convergence, if only at the center point itself. But there might be a larger interval, and that's what we're interested in. So let's actually look at that. So let's look at A. The series n goes from 0 to infinity of x to the n. To find IOC, we're going to use ratio test. So we know that for convergence, absolute convergence in fact, we need that the limit, remind me what the ratio test says. What limit are we looking at? The series when we plug in an plus 1 divided by an must be less than 1. Okay? So this would mean we need the limit of x to the n plus 1 over x to the n needs to be less than 1. Which means the limit, this cancels out, of x must be less than 1. But the limit as n goes to infinity of this is just itself. And now we have an interval of x values. This will converge as long as the range of x is less than 1. So that means x is between -1 and 1. Now, oftentimes we want to know, does it actually converge at these endpoints? So what we want to do now is check endpoints. If x equals 1, what would happen? Plug in x equals 1, I would get the series of 1 to the n, which converges or diverges? Diverges. How do you know?
Because it's just one forever.
Yeah.
So you could use the like nth term test.
Yeah, by the divergence test. Right? Limit is not 0. If x equals -1, then the sum I get is this, which diverges by, again, the divergence test. This means the interval of convergence is strictly between -1 and 1. It will only converge on that interval. So as long as you're within that range on your domain, this power series will converge, meaning it can give you a meaningful answer, meaning it's an actual mathematical object that we can talk about, we can study, and will give us meaningful answers to questions. So it's an infinite polynomial, whatever that might mean, but this is something that converges to an object. It's not like it's nothing. It's meaningless to write it down. It's actually meaningful to write it down as long as your x values are in this range. It's something that we want to consider. So in this case, what would the radius of convergence be?
1.
It's 1, right? So if you look on the interval from -1 to 1, clearly this series is centered at 0, the radius is just going to be that. So as long as that's the radius of convergence, that's the length of the interval on which it will converge. Here's a question. What does it converge to? Might take you a little bit of time to think about that, but it's... Let's say I put a 1 here. Does that help you? It's a geometric series. What would it converge to? My a is 1, my r is x. So what does it converge to? A over 1 minus r, right? We actually know that formula for a geometric series. And what would that be? 1 over 1 minus x. In other words, what I'm saying is, this infinite polynomial converges to something. It is a meaningful thing to write down. And what is that thing? 1 over 1 minus x. This is a function. It's a rational function, but somehow I can figure out how to express it as an infinite polynomial. We'll get back to that. Right? So the idea is, whenever my x is between -1 and 1, this function I can think of as that series. And they're interchangeable. Right? I haven't fully proven that yet, but that's where we're going. That's going to be the important part. Is the idea that I can express some random function that's not a polynomial as a polynomial of infinite degree, but it still behaves like a polynomial in a lot of the senses. In fact, because it's absolutely convergent, I know reordering the terms won't matter, and so if I differentiate it, I can differentiate the entire series, and if I want to integrate it, I can integrate the entire series. Let's do the next example. And hopefully you're realizing the potential here. There are some times where we're going to have very ugly functions to deal with, but we can use power series to turn them into very nice functions to deal with. And all we need to do is make sure where that function works, when will this thing be useful to use, and as long as it's useful, we can use what we know about the series to talk about the function itself. And it'll be a lot easier to deal with the function. B. Plus 1. X minus 4 to the n over 2n. Okay. So that is a power series centered at 4, where the coefficient term is 1 over 2n. So we wanted to find the interval of convergence, so again we use the ratio test. In Calc 2 it's always what you're going to use, the ratio test. So we need, for convergence, we need the limit, plug in this guy to the n plus first term, notice that has to be in parentheses, and divide by the nth term, which is going to be multiplied by the reciprocal. I would group these terms together, so this is 2n over 2n plus 2 times x minus 4 to the n plus 1 over x minus 4 to the n. This cancels that. The limit as n approaches infinity of this guy is going to be 1 because it's the ratio of the polynomials and the highest degrees of the top and bottom are the same, so it goes to the ratio of the coefficients. So this entire limit ends up just being x minus 4. And we need this to be less than 1. So this would mean, by the way, by what we know about absolute values, it breaks into that, which means I can talk about the range of x values for which this is going to work. I can add 4 to both sides. So this power series will converge on the interval 3 to 5. But we'd have to test the endpoints here. Let's look at the endpoints. Because the thing is, it might include the endpoints, it might not. It depends on the series, so you always have to check. So I know that's the interval that it's going to work on. So let's check the endpoints. So if my x is equal to 3, what I'm going to do is I'm going to plug in 3 into that. And the series would become minus 1 to the n over 2n. Which converges or diverges? It's an alternating series. So we probably want to use the alternating series test. So I'd look at 1 over 2 to the n. The limit of that is 0, and it is decreasing. This converges by the alternating series test. What about if x is equal to 5? Then my series becomes, I'm going to go to the original series, plug in x equals 5. I would get 1 over 2 to the n, which diverges because it's harmonic. Right, looks like the series for 1 over n. So this would mean the interval of convergence is the following interval. It converges at 3, but it does not at 5. So at 3 it works, but at 5 it doesn't work, but everywhere in between it will work. What is the radius of convergence? It's 1. Right? Remember, it's centered at 4. So if you're looking on the interval 3 to 5, the exact middle is 4, which happens to be the number that's here. Right? And the idea, the shortcut, I was going to say this later, but the shortcut, the idea here is if you can write as x minus some number less than, I'm gonna put the number over here, r, then this guy here is going to be your radius of convergence. So here I already have x minus the 4 is less than 1. 1 is going to be the radius of convergence. But figuring out the interval of convergence, I have to check the endpoints. Checking the endpoints involves doing the thing that we did on the test earlier today. So figuring out convergence is a part of this process. It's the part that involves checking the endpoints. So this power series makes sense. It converges to something that is probably useful on this interval.
And then if we were to write where it converged to, could we rewrite that? I guess we can't rewrite that as a geometric series.
No, that wouldn't be geometric.
Is there a way to do that though, that we want to make?
In general, there is no general method for doing that. It really depends on the problem. Not necessarily in this class, but in other classes, you will go into some techniques for that. But it's not. That's way up the chain. Probably in like an advanced calc class, you do that because the study of series is super important in advanced calculus. But you'll see all sorts of tricks, and we will see some things here, but nothing that we can turn into like a general method for figuring out what some series converges to. That is actually a very hard question to answer in general. Like in general, series do not behave very nicely. In fact, there are times where we can get an answer in terms of a series, but to actually say what function it gives us as a result is pretty much impossible. One place we're going eventually is, I mentioned this to you earlier in the semester, that has no antiderivative. But it turns out we'll be able to write that as a series, and I'd be able to integrate it as a series, and I'd be able to get an answer as a series. I'd be able to get an answer as an infinite polynomial. But to say what that converges to as some function that we're used to thinking about in Calc 1 and 2, there is no answer for that. There is no technique that you can finesse it with to get something like what we did last time, to get 1 over 1 minus x. So there are some nuances here. So we might get lucky and the series might be something that's nice, but it doesn't have to be. But the good thing is we often know, especially about what we'll talk about in Calc 2, the series we're going to form, we will know how to approximate within a certain degree of accuracy how good of an approximation there are. So at the end of the day, finding the right answer doesn't really matter, right? It just matters that we can get as close to the right answer as the context calls for, and that's good enough. So you won't always be able to write down, oh, it's this nice answer right here. That's very wishful thinking. It doesn't happen very often, especially not in practice, least of all in a calc class. So yeah, here, biratio test. We would be able to say that if we need the limit x to the n plus 1 over n plus 1 factorial times this less than 1, this means the limit x to the n plus 1 over x to the n times n factorial. Remember, n plus 1 factorial, just n plus 1 times n factorial, this will cancel. And so basically now what we have is the limit of x divided by n plus 1. And what is that? Remember, the limit here cares about the n. As n goes to infinity, what happens to that expression? Goes to 0. Which, by the way, is less than 1, literally always. So what does that tell you about the interval of convergence? Yeah?
Did that not like depend on what the x was, like if the x went to infinity and the n went to infinity?
X equals infinity is not a viable option, right? Like if you're plotting a function, you have to plug in a real number at some point. So at any point where you want to evaluate the x value, you're going to be plugging in some finite number in there. So it's going to be a finite number divided by something that's growing. So it turns out that this will work on the entire real line, which also means there are no endpoints to check. The radius of convergence is actually everything. Because when I take that limit, I get 0. Is that less than 1? Yeah, it's literally always less than 1. Right? So this leads us to some of the situations here. Given a power series, write it as Cn x minus x naught to the n. There are 3 possibilities for its convergence. One, the series converges only for x equals x naught. That's kind of the case where you try this limit and you end up with an answer that's bigger than 1. You can't make it. So if you did this limit and you end up with the answer 2, 2 is never going to be less than 1, which means I will never be able to get this thing to converge, which means it's never going to converge unless I plug in a value for x that makes the thing 0. And so that would be the center value, 2. The series converges on the entire real line. I.e., the IOC is negative infinity to infinity, and the ROC is infinity. It's an infinite radius of convergence. Or 3. The series converges only on some interval of finite length r given by x minus x naught less than r. R equals the radius of convergence in this case. So these are 3 possibilities for any power series. So in some sense, depending on the x value, the series will always make some sort of sense to us. So it'll either converge only for if I plug in x equals x naught, which makes it just me adding a bunch of zeros together. Converges, but not very useful. It is possible that it will converge everywhere, meaning you plug it into the ratio test and you get a value that's literally always less than 1, which means regardless of your x value, it will work. Or there is some finite interval on which it works, and you have to kind of test the endpoints. You must test the endpoints in this case. So we saw that this series makes sense on the interval from -1 to 1, not including the endpoints. This one makes sense from 3 on the interval 3, 5, where 3 is included. This one makes sense literally everywhere. Spoiler alert, we're going to figure out that that actually converges to the function e to the x, which means that's going to be another way to think about e to the x, which kind of means this is sort of going to the bonus. E to the x squared I can think of as a series by just plugging in x squared into that. So I can write e to the x squared as an infinite polynomial. That's kind of where we're going. But this is the basic it's one takeaway from this section. And how you would actually discover these things, very typically, it's going to be the ratio test. It's always what we're going to use, because it's a nice test that gives us absolute convergence, and it has an interval kind of built into it, right? Because there's some absolute value less than 1, which we know we can unfold into an interval all the time. So it's a very nice test to use. So a power series is a way to write an infinite polynomial. Sometimes these guys converge to nice things, and sometimes we can determine what they converge to and use manipulation of the series to manipulate the function itself. And that was in that section. And so that brings us to the next section, which is talking about representing powers by power series. So this section doesn't deal with the idea in as general as we will do it when we get to Taylor polynomials, because that's what a Taylor polynomial is. It's a formula that tells you how to express a function as a power series under pretty loose conditions. But in this section, we're really going to be looking at patterns, and if we know a series, we can figure out other series. We saw that the series of x to the n, for example, is equal to 1 over 1 minus x for x less than 1. Moreover, this convergence is absolute. This gives us two important facts, right? That we can only do with absolutely convergent series. We cannot do, we can only do this for absolutely convergent series. But the idea is we can start doing calculus on these series. And it means that if I take the series of x to the n and I want to integrate that with respect to x, it is the same as taking the integral of x to the n with respect to x and then taking the series of that answer. And if I wanted to differentiate with respect to x this series, it will be the same as differentiating x to the n and then taking the series of those terms. And that's because the integral of a sum is the sum of the integrals, and the derivative of a sum is the sum of the derivatives. And we know for absolutely convergent series that when we break it out and write it as an expanded sum, rearranging the terms won't matter, so nothing is going to mess with the value of your integral or your derivative. For a conditionally convergent series, that's not true, because when you get to this step here, your derivative, if you mess with it, now you change the answer. And so you get these two, right? So, and by the way, that's a general statement in general. If the series of an converges, absolutely, we can take the integral with respect to n as the sum of the integral with respect to n and the derivative of the series is equal to the series of the derivatives. We call this not very sophisticated, but we basically describe it with the process integrating or differentiating term I term. So the idea is, if I know the power series for a certain function, I can figure out what the power series of its integral or its derivative is, and I can keep doing this for as long as I can take integrals or derivatives of the function. So for example, I'll give you one example and we'll do some more next time. So for example, what is the integral of 1 over 1 minus x? Right, minus ln of x, right? So in other words,
Is it supposed to be 1 minus x, not absolute value?
oh, in the absolute value, yes, 1 minus x, 1 minus x. In other words, we can find a power series for ln of 1 minus x. By integrating the power series for 1 over x. So just by the fact that I know how to express this as a power series, I automatically know how to express an ln as a power series. So the idea is minus ln of x minus 1 would be equal to the series of the integral of x to the n dx plus some constant. And so that's going to be, if you integrate this, this is just x to the n plus 1 over n plus 1. This is n equals 0 to infinity plus some constant. And by the way, you can actually figure out what that constant is by actually plugging in the x value that you know about on both sides. So for example, if I plug in x equals 0, the left side would give me minus ln of 1, which is actually 0, and that would give me the series of 0 plus c, which means that my c is 0, which means that series is actually the entire answer, which means I can express that ln as an infinite polynomial. This means minus ln of 1 minus x equals this polynomial. X to the n plus 1 over n plus 1. In other words, I can look at negative of ln of 1 minus x as x plus x squared over 3 plus plug in 2 x squared over. Plug in n equals 0, you get x, plug in n equals 1, you get x squared over 2 plus x cubed over 3 plus x to the 4th over 4.